Good. So today we're scheduled to finish up on chapter 9, I think. It's chapter 9, yes, which is about aldehydes and ketones mainly. And we've said already that aldehydes and ketones, here's a generic aldehyde or ketone over here, like to undergo addition reactions with various nucleophiles. And that's going to be the main type of reaction we're going to be talking about. And these reactions go either by the nucleophile attacking the carbonyl carbon and breaking the carbon-oxygen pi bond, so it goes from a double bond to a single bond, followed by protonating the oxygen atom, or it could go the opposite way. It just depends if we're an acidic medium or alkaline medium. And we'll see examples of both of these, I think, today. But sometimes the proton goes on first and then the nucleophile attacks. Either way, the end result is the same. You get an addition product of this type. And we've only just scratched the surface of these. The one example of a reaction of this type that we've, I forgot a bond, shame on me. That's better. The one example of a reaction of this type that we've gone over is the hydration of aldehydes and ketones, where we said you can use either aqueous acid or aqueous base, doesn't matter which. This reaction actually is reversible. So if you have any of the addition product, the aldehyde or ketone hydrate, that can actually go back to the aldehyde or ketone. But that's an example of this type of reaction. And as I think I mentioned, not a particularly useful example. This is actually something we ordinarily take steps to prevent from happening, because the ketone or aldehyde is a known commodity. It's something we know how it's going to behave. Once the water adds and you get this, the structure's changed and it's no longer going to react that way. So we're trying to prevent the aldehyde and ketone from doing this just by reacting with water that's present in the air as water vapor. So we ordinarily use a drying agent or something like that. Keep the bottle tightly closed, make sure that no water can get in. That's normally what we do. But this is a good reaction to start with because it illustrates what we mean by an addition reaction to aldehydes and ketones. So we've already gone over these. I will just say a couple of things about the material today. I'm going to go a bit out of order from your textbook because, to be honest, while on most things I kind of like your textbook, the order that they present things in this chapter absolutely baffles me. I don't think it makes any sense at all. They do like one or two of these reactions and then cover hydration. I think that should go first because it's the simplest one. And so I'm going to go a little bit out of order from what's in the book, but the front of your chapter 9 class notes will say which are the sections of chapter 9 that you'll be responsible for. And then that's, of course, the other thing. Several of the sections of chapter 9 you won't be responsible for. So please do check at the beginning of the class notes for chapter 9. It does say which are the sections that you're not responsible for. And if it's not in the list of sections you're not responsible for, then you are responsible. But I think we're going to cover we will have covered pretty much everything else. When we're done talking about just a couple of reactions, I really only want to talk about two types of reactions, addition reactions of aldehydes and ketones with nucleophiles. Then we'll move on to reduction of these carbonyl compounds. We'll learn about a couple of really useful reagents that we'll also use later on in the term, so it's worth our spending some time on them. And I think we might already have talked about oxidation of aldehydes. That could have shown up even in chapter 7 when we talked about the reactivity of alcohols. But I just want to make sure that I've covered it. I won't have a whole bunch to say. And then when we're done with those things, we'll call it a day. That's pretty much what I'm planning on for today. So first of all, what about an example of this type of reaction that's actually useful? And it turns out that we can make, I already wrote cyanohydrin formation, but I'll repeat it. It turns out that we can make a class of compounds from aldehydes and ketones known as cyanohydrins. And we'll define that term with a picture, with a structure, once we get to that point. But it turns out that you can treat any aldehyde or ketone, and again, I'm being real generic here. I'm not saying what are the groups attached there. They can be either hydrogens or alkyl groups. But you can treat an aldehyde or ketone with hydrogen cyanide, HCN, and with a little bit of base in there. So HCN in water with just a catalytic amount of hydroxide base. And what you will get is a type of compound known as a cyanohydrin. What is wrong with me? OH. So the definition of a cyanohydrin is a compound of this type. It's an sp3 hybridized carbon that's attached to a cyano group or nitrile functional group, and also an OH group. Any compound of that type is what we call a cyanohydrin. And so just as an example, let me make up a couple of examples. If we were to take benzaldehyde and treat it with aqueous HCN, that says H2O, though you'd be hard pressed to know that. That's better. With a little bit of OH minus, then I would expect that you would get as the product the corresponding cyanohydrin of benzaldehyde. So you see, in order to get from the starting material to the product, you just change C double bond O to C single bond OH. You go from C double bond O to C single bond OH, and then you attach a cyano group, which, by the way, I should probably just remind you what that looks like. Don't forget that a cyano group has a carbon-nitrogen triple bond. So please don't forget the structure of the nitrile functional group. Cyano, nitrile, rather, same thing. Yes. Well, all these bonds are kind of equivalent. So yeah, you could also draw it like this. Same compound. So I think the one-word answer to your question is no, it doesn't matter. Good, so yeah, same compound. If you were to take, let's say, cyclopentanone and treat it with HCN with a little bit of aqueous base, I would expect that you would get the cyanohydrin of cyclopentanone, which would look something like that. And just to give another example, because examples are free, if you took 2-pentanone and treated it with the same reaction conditions, I would expect that you would get that cyanohydrin. And these reactions are usually pretty fast, pretty high yielding, no real problems. They're not generally problematic. And cyanohydrins are actually useful in their own right because now there's things you can do with the cyano functional group. We'll learn about them in chapter 11, I believe, later on, or maybe it's 10 or 11. I think I mentioned it in your class notes. Well, I could also look at your syllabus. That would let me know. After this, we're doing 16, which is in carbohydrates, which is going to be very well timed. Yeah, it's chapter 10. So we'll learn about some of the things you can do with nitriles in chapter 10, since that belongs in the discussion in chapter 10, much more than in this chapter. Again, mechanism is not something I want to emphasize real heavily in this class, but the mechanism here is simple enough. It's only 2 steps, so I don't mind showing you. Plus, you do get to do some practice with mechanisms in OWL, and I want to at least equip you to be able to handle them, even though there are sometimes problems with the OWL mechanisms. They're a little bit, again, persnickety in terms of exactly where and how you put the arrow. Whereas in real life, we're a little bit more flexible as long as the arrow starts and ends in the right place. It's all good. But I did it with acetophenone in your class notes. Let's actually do it with, I'll do a different one here in lecture. Let's talk about the mechanism of the cyanohydrin of cyclopentanone. So if we here had our HCN, the OH minus in the HCN is going to react to produce some of the cyanide ion, which looks like that. So that's that same cyanide ion that they're putting into people's coffee and murder mysteries, and then the person dies. So it's very, very, very toxic. I know I always give the same disclaimer. I'm no biochemist, but my understanding is the cyanide ion does the same thing as carbon monoxide. It gets into the heme site in hemoglobin. And so even though you're breathing in oxygen, it can't get into the heme site because the cyanide ion's stuck in there and doesn't come out. And there are, I believe, antidotes that if someone who has got cyanide poisoning, so if someone's been poisoned with cyanide and they find out soon enough, there's time to administer the antidote and save the person's life. Somehow it clears out the hemoglobin. But we need the oxygen to get in there, not cyanide. Cyanide gets stuck in the heme sites. Anyway, the mechanism occurs by attack onto the carbonyl carbon first. So you can see we're forming a new bond between the cyanide carbon, which is a minus charge. So this is our nucleophile. That's going to attack the carbonyl carbon. We break the carbon-oxygen pi bond and make a carbon-oxygen, go from a carbon-oxygen double bond to a carbon-oxygen single bond. So you would get an intermediate that looks like this. This will line up pretty well with what's in your class notes. Also, I just did a different example in the class notes. And then after that, recall that water is amphoteric. Water can be used water can either give up a proton to make OH minus or accept a proton to make H3O plus. And here it's going to give up a proton to make OH minus. So the oxygen with the negative charge will pick up H plus from water, and you'll get, again, the cyanohydrin, same product that we talked about over here. So it's only 2 steps. We won't do the mechanism of hemiacetal and acetal formation. That's got a bunch of steps, and I don't want to go into all the details with that. But this is a simple example of a nucleophilic addition to aldehyde and ketone carbonyl groups. It's a reaction that's actually used in the real world because, again, there's you can convert the nitrile functional group to a primary amine pretty easily, CH2NH2. That's very easy. It's just a reduction reaction. You can convert the nitrile to a carboxylic acid functional group. And as I said, we'll learn about some of these reactions when we finally get to chapter 10. But I figured this was a good example of a reaction that's actually done in the real world and actually is useful and is something that synthetic organic chemists might actually want to have happened as opposed to this hydration one over here. So bottom line, what you need to know is that HCN in the presence of aqueous base will add to an aldehyde or ketone to give the corresponding cyanohydrin. Cyanohydrin meaning you've got an sp3 hybridized carbon that's bonded to a nitrile functional group and an OH group. And in order to get the structure of the product, you look where the C double bond O is. You first find that. You convert C double bond O into C single bond OH. And then you'll need another bond on that carbon for it to obey the octet rule. So you just attach the nitrile or cyano group, and then your carbon will evade electrons around it. And that's basically it. That's cyanohydrin formation in a nutshell. Good. Make sense? Questions on any of that? Well, I need a little bit more space. So, oh, wrong one. Okay, so I just want to do one more reaction of this type. It's a little more complicated because it is several steps. Like I said, you're not going to be responsible for the full mechanism. It's quite involved. But understanding the steps, I think, will help you to understand the reaction as a whole, even if we're not learning the mechanism. So, and that has to do with the formation of hemiacetals and acetals. And we've actually already run into the word acetal in our chapter on nucleic acids. We said that in forming a polynucleotide, or really any nucleotide, sorry, I just lied to you. In forming any nucleoside, we need to form an NO-acetal between the nitrogen base and the ribose or deoxyribose sugar. So that's something we've covered already. I think that will make a little more, even more sense now in context when we actually talk about acetals. And acetals are also going to be pretty important to us in chapter 16, which we're going to get to next, which is going to be on carbohydrates, because you find acetal functional groups very commonly in simple sugars and even in more complicated sugars with more complicated structures. So just as well that we learned something about both hemiacetals and acetals. So in forming a typical hemiacetal or acetal, we'll again start with generalized aldehyde or ketone. So these bonds can be to either hydrogens or alkyl groups, doesn't matter. Both will work fine. And what we're going to add is, I'm drawing this a little different than in your class notes, but it's the same concept, and I think it might be a little simpler this way. So we'll see which way you like better. What we're going to do is we're going to heat the ketone or aldehyde in the presence of an excess of an alcohol, meaning that we're going to have more than one mole equivalent or more than one molecule of the alcohol for every molecule of the ketone or aldehyde. In fact, probably we'll just use the alcohol as the solvent. So there could be 100 or 1,000 mole equivalents of the alcohol in comparison to the ketone or aldehyde. You also do need an acid catalyst. Probably it'll be a little bit of sulfuric acid or phosphoric acid. And then you also need to heat it. And you can write heat, H-E-A-T. If you ever see a triangle like that, that's an abbreviation for heat. If you see two triangles, it means heat very strongly. But just in case you ever run into that abbreviation so you know what it means, if you ever see a triangle in that context, it just means heat. And in the first step, you will get a structure that looks like this. And we call that a hemiacetal. And the definition of a hemiacetal is an sp3 hybridized carbon that's bonded to OH and an alkoxy group. So you have one of each. The hemi in hemiacetal is because one of them is still an OH group. And this will then react further since we have an excess of the alcohol. It will react with a second molecule of the alcohol. And so you wind up with the full acetal at that point. And acetal. And you'll also get a molecule of water out at the end. That's just going to be an inorganic side product. So, and of course, it doesn't matter where you put the ORs, as long as you have all four single bonds. I would expect in terms of, well, actually, there is no stereochemical issue. Sorry to go back to chapter 5 on you guys, but this carbon is not chiral because it is two of the exact same group on it. So there's none of that R and S stuff going on anyway. There's no stereochemical issue. So it doesn't matter which bonds you draw to the other two groups and which go to the alkoxy groups. But the definition of an acetal is it's kind of like a carbon with two ethers on it. So you have two different alkoxy groups on that carbon. That's the definition of an acetal. And it has to be exactly like that. The two alkoxy groups have to be on the same carbon. So the way this works is at first one molecule of the alcohol reacts with the aldehyde or ketone, you get the hemiacetal. This will then react further in most cases, especially if there's an excess of the alcohol. In cases like that, you will wind up getting the full acetal from the hemiacetal and generating a molecule of water. So it's a little bit more involved than cyanohydrin formation, but it's the same type of reaction. This is still a nucleophilic addition reaction to an aldehyde or ketone. In the end, you get the result of two molecules of the alcohol adding to the aldehyde or ketone with loss of a molecule of water. So there's still a net addition of one molecule, I would say. And in the end, the type of product you get, again, in most cases, is going to be the acetal. So just to give an example, let's say that we took cyclohexanone, which would look like this. And let's say that we dissolved it in an excess of methanol with a little bit of sulfuric acid as the catalyst. That's your H+. You just need a couple drops. And you will at first get that intermediate. The square brackets means it's an intermediate, and it's, wait a minute, I just realized. Yeah, the square brackets means it's an intermediate. We don't need square brackets here. So please make that change in your notes. I put in square brackets where we shouldn't have had any. That's the final product. So the square brackets means it's not your final product, it's an intermediate. But that is the final product. So please cross out or erase those square brackets in the notes you were taking. I did that wrong. Here, this is a hemiacetal just like before. You can see OH and alkoxy, in this case, methoxy. So you will get the hemiacetal at first. This is going to react again with the methanol, so more CH3OH. In the end, you will get the dimethyl acetal. And you will also get a molecule of water. If you were asked to write a balanced equation, you'd point out that there's also a molecule of water. However, we're mainly focused on the major organic product, which would be that acetal. So once again, when we add our ketone, in this case, to our alcohol in the presence of an acid catalyst, at first we get the hemiacetal. That then reacts further with the alcohol, since there's an excess of the alcohol. And so you wind up getting the acetal, the full acetal out of that. Let me do another example. Let's say we treated with, oh, I don't know, butanal. And let's say we treated this with ethanol in the presence of excess methanol. In the presence of a little bit of sulfuric acid, I would expect that at first we would get the hemiacetal that would look like this. Of course, this hydrogen is still here. That used to be the aldehyde hydrogen. You don't have to draw it if you don't want to, but you can. It's not wrong. If we'd left it out, it would be understood that the hydrogen is still there because we're using line angle drawings. And that's going to be an intermediate. And then that will react further with ethanol again. By the way, have I introduced the abbreviation ET for ethyl? I might not have. You might sometimes see that ET. It just means ethyl group, CH3CH2. Another way you could also abbreviate it, C2H5OH. Perfectly acceptable. Everyone will know what you mean. Because if you take a look at this, I think you'll be able to convince yourself there's only one way to put together two hydrogens and oxygen, or sorry, 2 carbons and oxygen and 6 hydrogens. There's only one way. So it's unambiguous, C2H5OH. There's only one way to do it. But ET is short for ethyl group, if you ever see that anywhere. In any case, you would then have, see, I could have written OET over here. I just don't want to confuse you guys unnecessarily. But I just mentioned that in case you ever run into that. It's just a shorthand for an ethyl group. I've even seen ME for methyl group, though that never made a lot of sense to me. Methyl group is already just CH3. ME is not much of an abbreviation, but you might sometimes run into that as well. So just in case you do, it's not this weird element ET that you've never heard of. It's not the extraterrestrial element. It's just an ethyl group. So that's another example of the same type of reaction. And I would expect at the end you would get the diethyl acetal. Again, that hydrogen is still there. It's understood. That was originally the aldehyde hydrogen. So, but with any aldehyde or ketone, you'll quickly and easily get the acetal, maybe not so quickly, but pretty easily by, oh, I forgot to write heat, H2SO4 heat, H2SO4 heat. This does usually go much faster when you heat it, but it's generally a pretty easy reaction to accomplish. I would say the reaction is driven forward by Le Chatelier's principle. If I may be allowed to bring up something from Gen Chem, one of the things Le Chatelier's principle says is you can drive, because it is an equilibrium, these are reversible steps. And one of the things Le Chatelier's principle says is that you can drive an equilibrium forward, or you can drive a reaction forward by removing one of the products from the reaction mixture. And what effectively happens here is this molecule of water that you generate, it's as though we've removed the water, because as soon as you generate this molecule of water, it drowns in this ocean of the alcohol, methanol in this case, ethanol in this case. And so it'll be outnumbered by the alcohol molecules by several orders of magnitude. And so it's as if you removed it. It gets diluted into the alcohol so much that it's a non-factor. And so this reaction gets driven forward by as though you removed the water from the reaction mixture. There actually are ways of literally removing the water also. There are ways you can do that. You can add a drying agent, for instance. But even if you don't, this reaction will go forward pretty easily. Good. So if I can also be allowed to give an example from your book, it's possible for the alcohol and the aldehyde or ketone to be in the same molecule. One example your book gives is 5-hydroxypentanal, which would look like this: 1, 2, 3, 4, 5. So 5-hydroxypentanal. Not pentanol, pentanal, and that's because we're numbering 1, 2, 3, 4, 5. The OH group, which we're calling hydroxy, is on carbon 5. Carbon 1 is understood to be the aldehyde carbon. So you don't say 5-hydroxy-1-pentanal. As soon as you mention that it's an aldehyde, the aldehyde carbon has to be carbon 1. Because if it were not on the end carbon, then it wouldn't be an aldehyde, it would be a ketone. So let me redraw that molecule for you in a somewhat more suggestive manner. So if this is carbon 1, you have 2, 3, 4, 5. And you can see that the OH group in carbon 5 is in exactly the right place to attack that carbonyl carbon. And so whichever way you want to draw that molecule, you can draw it either way. If you were to treat this with just an acid catalyst, it's going to react with itself, and you will generate a hemiacetal that has a 6-membered ring. So this is carbon 1, 2, 3, 4, 5. And then the oxygen is the 6th atom in the ring. So this is not going to go on to form a full acetal. You'll just have the hemiacetal. And you don't form a water molecule. So you'll get, I'll even say, a cyclic hemiacetal. And what you want to look for formation of a 5- or 6-membered ring. Those are going to be the ones, I'll even say 5- or 6-membered ring only. You're not going to see rings of any other sizes. The reason is the atoms for forming a 5- or 6-membered ring, all of those atoms turn out to be just in exactly the right place. You can even kind of see it when you draw the intermediate like this. And so 5- and 6-membered rings are very easy to draw. Other ring sizes, not so much. But if there had been only 3 CH2s instead of 4 CH2s, I would expect, and what would that be? That would be like 4-hydroxybutanal, I guess that would be. Then you'd get a very similar looking thing, except it would be a 5-membered ring. But the reaction type is the same. In this case, you don't get a full acetal, and the way you know is because the alcohol is not in excess. The alcohol in this case is included in the molecule, and it's not in excess. There's one OH for every carbon-oxygen double bond. Or you know what? Actually, I like it. Let's even do a different example. Let's go crazy, as I like to say. Oops, I did it wrong. In order to go crazy, we have to do it right. There we go. 1, 2, 3, 4, 5. So I think this guy would be something like 5-hydroxy 2,1,2-pentanone. This will also line up very nicely. So this one's not in your book. 1, 2, 3, 4, 5, OH. And you can see again that OH group is in just the right place to attack. If you treated this with an acid catalyst, I think you would very easily get that 5-membered ring. So the carbons would be 1, 2, whoops. Sorry, that's more better. 1, 2, 3, 4, 5. There we go. That's better. So the carbon 1 is the methyl group. That's this carbon over here. And carbon 2 used to be C double bond O, now it's C single bond OH, just like all of these other reactions up here. So this is another example of the same type of thing, but forming 5- and 6-membered rings is quite easy. 4-membered ring, it can't quite reach. Same thing with 3-membered rings, not to mention they're also very strained. And 7-membered rings have the opposite problem. 7-membered rings, it doesn't quite reach into the right place, and everything's kind of flopping around, and it's just not in a convenient place to attack. So I won't say it never happens, but certainly for our purposes, we're not going to be running into it. So this is a way of getting a cyclic hemiacetal. But you want to look for formation of a 5- or 6-membered ring. I think any example you come across of this type of reaction, you're going to be forming a 5- or 6-membered ring only. I don't think you'll see any others. There's one other type of acetal formation that I want you guys to be aware of. It's also possible to make a cyclic acetal, and I'll get to that next. But I want to make sure everyone's copied this down first and is tracking. So any questions on any of this? Oh, yes.
For these cyclic hemiacetals, do we have to care about the carbon being chiral?
Oh, I don't think so. Or is that one chiral? I guess it actually is. Well, you would get a racemic mixture. You'd get both. You wouldn't get just one. So if you're asking, do you have to know which you get? No, you'd get both. Yeah, I'm confident. In cases like that where there's nothing particularly favoring one over the other, you'd get a racemic mixture. And that's pretty common. Good question, though. Other questions? All right, so one more thing in this category. It's also possible to form a cyclic acetal if you use a diol instead of an alcohol. So just to keep things relatively simple, let's take 3-pentanone. 3-pentanone. And instead of treating it with like methanol or ethanol, let's treat it with ethylene glycol, which is a molecule we met in chapter 7. It's an example of a diol. You've got multiple OH groups in the same molecule. And let's say that we have, again, an acid catalyst. Let's say we heat it. Just to make sure we press the point. At first, what you would get is a hemiacetal, which would look like this. So that's your hemiacetal. And you'll notice there's still an OH on the other end over here. So we can still lose a molecule of water and form a full acetal, which would look like this. And of course, you'd also get your molecule of water out. So hemiacetal over here, and that would then go on to react in again, we would call that an intramolecular reaction. Intramolecular meaning it occurs within the same molecule. Don't know if you'll run into that word again. But in case you do, it's like intramural. You know, it occurs within the same molecule. So, but it's not a different reaction. It's the same type of reaction. It just occurs all within the same molecule. And so once again, you want to look for formation of a 5 or 6 membered ring. In those cases, it's very favorable. And so this is still an acetal. And this is still a hemiacetal. If you compare to the structures we had earlier, you'll see it fits the definition. The only difference is instead of having 2 different alkoxy groups, you have it included in a ring. So getting 5 and 6 membered cyclic acetals is pretty straightforward to do, but it's not a different reaction. It's the same reaction, just set up to occur within the same molecule. So I wanted to get in an example of that type of reaction as well, but it's just another type of the same reaction. It's just another reaction under the same category, I guess I would say. Good, so I think that's all we need to say about acetals. The only other things I really want to cover are redox reactions. Well, before I do redox, let's talk first about reduction of aldehydes and ketones. Because as I've mentioned, it's going to teach us some reagents that we're going to use again later on in chapter 10, in fact. We're going to take a little detour after this chapter and do our chapter in carbohydrates, and then we'll come back to carbonyls and we'll cover chapter 10, which will be on carboxylic acids, esters, amides, nitriles, all those other types of compounds that have their own sets of reactions. But in any case, again, speaking very generally, I always like to do a general example first before we get in, or a general case maybe before we get into specific examples. If we have a generalized aldehyde or ketone, we can treat this with a reducing agent. Recall that H in square brackets means we're using a reducing agent. And the product that you'll get will look like this. So we've changed C double bond O to C single bond OH, and we've added a hydrogen to that carbon in order to round out the octet of electrons. So that's another type of reaction that aldehydes and ketones undergo very readily. And we have 2 different reducing agents that you'll need to know about. One of them is sodium borohydride, NaBH4. And the other one is lithium aluminum hydride, which this is done in a stepwise fashion. So the first step is lithium aluminum hydride. The second step is dilute aqueous acid. So you do have to number the steps. What the numbered steps basically mean is we add in the lithium aluminum hydride first, and then we wait. We wait until everything's done reacting, and then we add the dilute aqueous acid. So that's, if you see numbered steps like that, that's what it means. Numbered steps mean that you wait between the steps. You wait until everything's done reacting, and then you add the next material. You don't just dump it in all at once. Meanwhile, if it's not numbered, like with sodium borohydride, then you just dump it in all at once. So for aldehydes and ketones, these two reagents, sodium borohydride and lithium aluminum hydride, are interchangeable. They will have the same result. Both will cause the reduction of C double bond O to C single bond OH. They both will do that. The reason you need to know both reagents, though, is a couple of reasons. First of all, just conceptually, sometimes in practice you find a certain reagent will not work, and so you need an alternative. So that's, there might be 6 or 8 different ways to do a certain reaction. And you also know, thanks to Murphy's law, whatever you try first is not going to work. That's just life, So that's one of the reasons you need to know multiple reagents in cases like this. The other one is more practical than that, because as it turns out, once we apply reduction, the idea of reduction to esters or carboxylic acids or something like that, now these two, then these two reagents will no longer be interchangeable. Then it will matter which one you use. But for aldehydes and ketones, they're interchangeable. It doesn't matter which you use, same result. So just to give a few examples, if we took cyclohexanone, and let's say we treated it with LAH, as we sometimes call it, then I would expect that you would get cyclohexanol as the product. Whoops. Well, I can write the H in. Though I didn't have to. I chose to write the H in. So again, we change C double bond O to C single bond OH, and we add a hydrogen. That hydrogen actually comes from the lithium aluminum hydride. The other H, the one in the alcohol, will come from the water in the dilute aqueous acid. But that's one example. To give another example, I'm here using, well, let me make a little more room since I don't know why I'm being so stingy with space. Here's another example I got from your book. This is 2-butenal or something like that. 2-butenal. If you were to treat this with sodium borohydride, or I think with lithium aluminum hydride, I don't think it matters which one, I would expect everything else will remain the same. The carbon-carbon double bond will survive, and you'll get CH2OH. So of those two hydrogens, one was there to begin with, one was the aldehyde hydrogen, and the other one got added by the sodium borohydride. And then it will also pick up a proton from the solvent. The solvent's probably going to be water or aqueous methanol or something like that. So, it'll put the proton and the oxygen from the solvent. So that's another example of this type of reaction. If, let us say, I just want to do a couple more examples like this. If you used acetophenone, and we treated this with, let's say, sodium borohydride. By the way, let me teach you another abbreviation, not because I'm really concerned that you always use these abbreviations, but if you ever see pH like that, capital P, lowercase h, that means phenyl group, C6H5. You would get this alcohol. And in fact, you can write that also. You can write C6H5 here, perfectly acceptable. They're both acceptable abbreviations for monosubstituted benzene rings, because there's really only one reasonable way to put together 5 hydrogens, and 6 carbons. The only reasonable way to do that is a benzene ring with one of the hydrogens replaced with something else. So you don't have to use those if you don't want to, but in case you ever run into that in an OWL problem or something like that, this way you'll know what it is. I also just realized, I don't know how I did it, but I'm running out of time. I do just want to point out that that's pretty much it for reductions of carbonyl compounds. We already covered the oxidation of aldehydes. Just a reminder that you can oxidize an aldehyde with Jones reagent. And the product will be the corresponding carboxylic acid. But I think we already covered that earlier in the chapter. I moved it to the front where it made a little bit more sense. So with that, we're actually done with chapter 9. So very good. Have a great day, and I will see you all on Wednesday. I hope to have more news on the exam by then. I think I will. I think that will be the case. Have a great day. Certainly by the end of the week, you should know.